Greetings, mathophiles. Welcome to a video on a statistics concept that involves the measurement of the degree of spread in a data set. And that measurement is called the standard deviation. And there is a closely related concept called the variance. We're going to begin by looking at two different data sets that I hope I've made small and simple. They're ginned up for the purpose. So data set A, we have some values 1 through 6, and you can see the frequencies there in the table. Data set B, same story, values 1 through 6, different frequencies. And I want to begin by observing that data set A is a little more spread out in the sense that more of its values are at a greater distance from the center. And so as we look at finding ways to measure the degree to which a data set is spread, we should expect going in that data set A is going to have a greater measure on any meaningful scale of spread than data set B. And so we'll see by the time we get a little farther along whether that prediction is accurate. I tried to set these up so that there were a lot of similarities so that we could really focus on the meaningful difference, which is the spread. So if you count up the frequencies for both data sets, you find that there are 10 values in each case. If you add up the values, so in the case of A, for example, there are 3 1s, there's a 2, there's a couple of 3s, and so on. If you sum those up, you get 30, which means the mean is 30 divided by 10, or 3. Same thing down here. I wanted these to be identical so that we could really focus on the question of spread. One of the sort of first ways of measuring spread that you probably learn as a younger student is the range. And the range is just the maximum value in a set minus the minimum value in a set. And in this case, the range is 5 in both set A and set B. They run from 1 to 6. You may be aware of a measure called the interquartile range, which is a little more sensitive than the range as such. But it's not going to capture all that we ultimately want to be able to capture. But just for the record, the interquartile range here is 3. The interquartile range is 2. So a bit of a difference does begin to emerge when we start measuring spread a little more sensitively, comparing data set A and data set B. If you'd like to know more about interquartile range, we have a video on this channel that describes how to calculate it. I'll leave a link to that in the description for this video. Our task is going to be to try to find a measure of spread that is sensitive enough to detect small movements on the part of individual values in the data set. And what that means is probably we have to do a lot of arithmetic. One approach that you could take would be for each value to find its distance to every other value and take some kind of a sum or some kind of an average of those distances. Even in the digital age, that sounds a little bit unreasonable, and certainly in prior times when these concepts were being developed, that would have been completely out of the picture. So what's done instead, and you don't lose anything by this as it turns out, what's done instead is we compare each value in the data set to the mean of the data set. So we said a moment ago, we're doing this for data set B, we said a moment ago that in both cases the mean was 3. And so what we can do is we can go through and find the distance between each value in the data set and the mean of all the values in the data set. And we'll just do that by subtracting. In principle, you could subtract in either order, but the standard thing, the customary thing, is to take each value minus the mean rather than the other way around. These differences are called deviations, or deviations from the mean. And so we'll just go through and do this. So 1 minus 3 is -2. We get some -1s. 3 minus 3 is 0. And we got a couple of 1s, and we've got a 3. And you might think, all right, we could just add these up, and that would be some kind of measure of the spread. Except when you add up deviations from the mean in a given data set, you always get 0. This can be shown algebraically pretty easily if you have some skills with summation notation. So If that's not going to give us a different result one time from another, then what do? We could take the absolute value. That would be a perfectly valid approach. The thing that is done, and we're not going to explore the reasons in this video, it's a little bit beyond us right now, but the thing that is done is that you take the squares of the deviations. And they're just called the squared deviations. And so I run down this third column and I square everything. So I've got a 4, I've got some 1s, I've got some 0s, I've got some 1s, and I've got a 9. And when I do all of that arithmetic, I get a sum of 18. And that begins to capture how spread out these values are. But there are some issues with it. And the most glaring of which is that it really is also, to a large degree, a measure of how many values there are in the set. If I were to simply insert a few more values, and maybe even values near the middle, this number would climb, and maybe we wouldn't want that. So maybe it's better to take an average of the squares of the deviations, and that's the thing that is done. So I could take these deviations, square them, add them up, and divide by how many there are. Essentially take a mean of the squares of the deviations. And if I did that here, I would have the 18, there were 10 values, and so I would get 1.8 for the average of the squares of the deviations, the mean of the squares of the deviations. This has a name. This is called the population variance. And variance, getting at the idea that we're trying to measure how much things vary. There is a bit of an issue with this in that this now is in units that are the squares of the units in the original data. And so if we were measuring things in feet, for example, then this would be in square feet. And it might be odd to measure this degree of variability in a measure of length using a measure of area. And so what more frequently is done is that you don't stop here, but you want to take the square root. And that gets you back to the same units as your original data, and that is called the population standard deviation. So that's just this stuff with a square root sign over everything in sight. So it would be the square root of the sum from I1 to n of the squared deviations all over n. This covers the whole thing here, the square root. And that would be, in our case, the square root of 1.8. And the square root of 1.8, I wrote it down somewhere, is 1.34. So that's the population standard deviation. There's a symbol for this. It's a lowercase Greek sigma. And it would then only be logical that the symbol for the population variance would be the square of that sigma. Now, these statistics introduce a slight issue, which is that they somewhat underestimate the variance in a population when you're using numbers from a sample. And we're not going to push too deeply into what that's all about either, except to say that it's a thing. And there's a relatively easy fix. And the relatively easy fix is that in both of these cases, rather than dividing by n, you divide by n minus 1. And so if we were looking at values that were from a sample, we would be talking about the sample variance and the sample standard deviation. And we would be dividing by n minus 1 rather than n. And before the end of the video, we'll flash sort of a grid that shows all 4 of these organized in a way that I think you will find helpful. Just by way of comparison, set A, which we said was more spread out, set A has a sum of squared deviations of 28. Rather than the 18 that we saw up here. So, at least in that simple head-to-head comparison, we find a situation in which our measure of spread, or at least the basis for our measures of spread, is higher in the data set that we consider to be more spread out, which is an encouraging thing. Notice also that if all the values in the data set were the same, then the mean, of course, would be equal to whatever that value was. The deviations would all be zero. And so all of these statistics, the sample and population variance, the sample and standard deviation, would be zero, which is what you would like in a measure of spread. If there's no spread, you'd like your measure to be zero. Before we move on, let's just briefly return to the graphs of these two data sets and compare them across all of these various measurements that we've just discussed. As we mentioned, the sum of the squares of the deviations was larger in A. It was 28 as compared to 18 for B. And because all of the other statistics, the sample standard deviation, sample variance, population standard deviation, population variance, depend on the sum of the squared deviations, it will be the case that all of those measures are greater in A than in B, which reflects the greater degree of spread in A than in B. Here is a different look at our data set B. These are the same values that we were examining a moment ago, entered into a Desmos file. And off to the left, you'll see two values, the population standard deviation and the sample standard deviation. It shouldn't be surprising that the sample standard deviation is somewhat greater because it involves a division by n-1 rather than a division by n with the same numerator. And what I want to do is just play with the degree of spread in this data set. So I've got a slider that just applies a scale change to these values. And you'll see that as things spread out, these things that we decided were potentially good measures of spread get bigger. And as we draw things more closely together, they get smaller. And so that should provide some additional sort of intuitive grounding for the notion that we have hit upon statistics that are going to be effective at doing what we're expecting them to do. You'll see now on the screen a sort of a table with the four formulas for these four different statistics. And if you sort of encountered those formulas in the wild, they might look a little bit daunting, but I encourage you to unpack them a little bit as we've been doing in this video, because I think that what you'll find is that if you understand how they're put together, they're much easier to remember and it's easier to figure out which is which. They're all based on the sum of the squares of the deviations. And fortunately, we didn't have to calculate these deviations and square them and so on because we have digital gadgets that'll do all that for us. And if you are a user of TI-84 calculators, we have a video on how to get these values out of your calculator, and I'll post a link to that in the description as well. But then it just breaks down according to whether you're dividing by n or by n-1. Is it a population that you're an entire population you're dealing with, or is it a sample taken from a population? And is your interest in the variance or the standard deviation? There are uses for the variance. We're not going to discuss them here. It's more typical to use the standard deviation in a situation where you just want a measure of the spread that is present in your data set. So I hope this has been a helpful introduction. And I hope that you find it less mysterious now to be in situations where you encounter standard deviations. You'll have a better sense for where they come from and what they're about and what they're supposed to do. Happy mathing.